work by energy, what we had started with in the last lecture. So this is session number 2 for us. So quick recap, what we had learned is work done by a force is defined as the path integration of F dot ds, force over displacement, from initial to final position. Okay. And if the force is constant, then this integration of F dot ds automatically reduces to F dot s. Okay. But that's only if the force is constant. And what we mean by constant is both magnitude and direction are constant. Both in magnitude and in terms of direction. Both these things. Okay. So that is the first thing we learned about work done. And then we saw that the net work done by the sum of forces acting on a body equals to the change in its kinetic energy. This is the other theorem that we had seen. Okay. So net work done is algebraic sum of work done by all forces. Okay. And change in kinetic energy is defined as half mv square minus u square, where v is the final speed and u is the initial speed. Okay. So let us start with an example or two of the application of this work kinetic energy relation. So this over here is called the work kinetic energy theorem. So let's begin by looking at an example of this. So now in this example, we have a situation wherein there is an irregular slope like this, okay, such that it's a smooth surface. Gravity is acting like this. Okay. Now this distance is small d from here to here, and this distance is h. Now body of mass m or a particle of mass m is at rest at the point A initially. And what happens is we continuously apply a force, a constant force, horizontally on it. So this constant force ends up pushing the body along the surface. It makes sure it doesn't lose contact, and it pushes it along the surface so that eventually it reaches the point B over here. By the time it reaches the point B, it has a speed v. So everywhere this force is acting continuously on the body. Okay. So a particle of mass, let's say 5 kg, at the point A, initially at rest, okay, is acted upon by a constant horizontal force F of magnitude, let's say 40 newtons, as shown. Find its speed v at the point B, given that d is equal to 100 meters and h is equal to 20 meters, and the surface is perfectly smooth, so there's no friction involved. Okay. So just see how you'll make use of these two definitions that we've discussed, the work done definition and the relation between work and kinetic energy, to come up with the solution of this. Because as you can see, it's not a straight inclined plane. So we cannot use Newton's laws and find the acceleration and then use kinematics. We have to use the work kinetic energy relation. So see how you will utilize these formulae and come up with the solution of this. So this problem will give us a very interesting example of a situation in which work energy theorem or work kinetic energy relation gives a very simple solution to it. But at the same time, the problem is not solvable by Newton's laws, because we cannot do the vector analysis here. Why we can't do the vector analysis? Because the angle of inclination is continuously changing, and we don't know how that angle is changing. So there's no way we can do vector analysis and use Newton's laws and kinematics. The only way we can solve the problem is by doing the scalar analysis using work and energy. Anybody got the answer for this? See, as the particle is sliding up now, because we are forcing it with that external force F. Just write this force as F. Okay. So there are three forces which are acting on the particle at any point of time. You can understand that as it is going here. You look at the particle during any small displacement like this from here to here. So during this differential displacement of ds, the forces acting on the particle are three in number. There is this external horizontal force that the external agent is applying. Okay. So that is there. Okay. There is the gravitational pull of the earth, which is like this. And then there is the normal contact force that the surface is applying on it, which is like this. Now, if you were to compare this situation with any other time, now let's say the particle is after some time over here, it's making a displacement to this point, you will see that the only thing which has changed is the normal reaction force. And luckily for us, it has changed in such a way that it again becomes perpendicular to the ds. So at any instant of time, the work done by normal reaction is zero, even though it's a variable force. And the other two forces are neither changing magnitude nor changing direction. So we can calculate the work done by them by just using simple dot product method. So the other two forces here, which are the external force F acting horizontally, and this one. So you can see that everywhere the differential displacement and the normal reaction will be perpendicular to each other. Okay. Whereas the other two forces mg and F remain constant. So now going from A to B, so the theorem we'll use now is that the net work done is equal to the change in kinetic energy. So the net work done should be equal to the work done by mg plus the work done by F plus the work done by normal reaction. Now work done by mg, this dot product, you can see if this is H and this is D. So you can write the displacement as, taking this as X and Y, we can write the displacement as di cap plus H j cap. You can write mg as a vector as minus mg j cap. You can write F as a vector as some constant quantity F I cap. Okay. So next step, this will become minus mg H plus F dot S. Okay, so next step, this will become F into T. Okay, but this will be integration of n dot ds, and this step, next step will become 0. So the net work done is this much. The left hand side of the equation, net work done is this much. Okay, that's what makes this problem very easy to solve using work energy. Now why n dot ds is 0 integration? Because n is perpendicular to the differential displacement at all points during the path. It's always normal to the surface and ds is tangential to the surface. So n is normal or perpendicular to the surface. And ds is tangential. Yeah, guys, I was muted because some call I had to attend. Anyway, so now that is done. So main thing you understood this now, that why this is always perpendicular, because why normal reaction is perpendicular to displacement always, because normal reaction acts normal to the surface and ds is tangential, so always the angle between them will be 90 at every point you can see. Okay, whereas mg and f are constant forces. These are constant forces, so their work done will be calculated by dot product method, you see. Okay, so this is the left hand side of the equation, net work done. On the right hand side you can see u is 0 at a and we have to calculate the speed v at b. So right hand side of the equation will now become RHS, the change in kinetic energy, that become half mv square minus 0, because u is equal to 0 at the point A and v is equal to v, which we want to calculate at the point B. So this will just become half mv square. So net work done equals to change in kinetic energy will now imply that FD minus mgh should be equal to half mv square. So from this we will now calculate the value of v. Okay, just substitute the values I had given earlier to calculate the value of v. I'll just pick up these values and show you. Okay. M is 5 kgs, D is 100 meters, F is 40 newtons, and H is 20 meters. Okay. So M was 5 kgs, D is 100 meters, H is 20 meters, F is 40 newtons in magnitude, and take G as 10 meters per second square. So from this you'll get the value of V. Just calculate the value and tell me how much it is in meters per second. Okay, very good. Kunal and Yash, that's correct. Okay. So you have to just substitute the values. So 40 into 100 minus 50 into mg is 50 into 20 is equal to half into 5 into v square. So v square is becoming 2 by 5 into 4000 minus 1000. So that's 3000. So that's 1200. So v is equal to square root 1200. So that is 20 root 3 meters per second. You can take root 3 as approximately 1.73. So 732 whatever. So this is approximately okay. Yeah, 20 root 3 is the correct answer. So 34.6 or 34.64 whatever, that's any of these answers are fine. You can leave it as 20 root 3 also at this stage. Okay, so now you see the advantage of the work energy relation or the relationship between work and kinetic energy, a problem which is virtually impossible to solve by Newton's laws because we cannot do the vector analysis because the angle of inclination is continuously changing. Now we can do that quite easily using work energy theorem or work kinetic energy relation. Okay. Now next we move on to very important concept of something called conservative and non-conservative forces. So this I'm guessing will be new for you. You may not have heard the term conservative or non-conservative forces before. Okay. Now, as we know, the work done by a force in general is defined as the path integration, F dot ds, integration from initial to final. This is how we define the work done. So if we are going from one path from the point A to B, let's say, okay, then at every point during the path we have to integrate the dot product of the force with the displacement from point to point. And point to point, the force might also be changing. So it's instantaneous value of force integrated over the path. Okay. Now in certain cases, Krish, I'll go back to that later. Okay. Now in certain cases, what will happen is that if I go by a certain path, the work done might come something. Now if I go by a different path, but to the same point, okay, now the integration might result in something different or it might result in the same value. It all depends on the type of force we are dealing with. So if I take a body or a particle or whatever by two different paths, while that force is acting on it, if the work done is the same every time, no matter what path I take between A and B, then we call it a conservative force. Whereas if the work done is going to depend on which path I've taken, then the work done will become a non-conservative force. So if the work done is what we call path independent, what it means by path independent means that should be identical for all paths. Any path we select, it should be identical between the same initial and final position. Okay, then we say it is path independent. Whereas if the work done is path dependent, by path dependent it means that the work done can be different for two different paths. Okay, obviously between the same initial and final position. Okay. So if this is what is happening, okay, if the work is path dependent, then we say the force is non-conservative. Okay, we define it as non-conservative. Whereas if this is what is happening, the work is path independent, it's always the same for whatever path, then the force is what we call a conservative force. So definition of conservative force is that the work done is path independent, and definition of non-conservative force is that the work done is path dependent. So just make a note of this point first, then we'll continue ahead with this, with examples and things. Okay, you can finish writing this down in case something is remaining. Then come back to the definition of conservative and non-conservative forces. Okay, Krish. Now come back to the definition of conservative and non-conservative forces. So next up, we'll discuss an example or two of each. Yeah, so actually that depends on the nature of the force. Now that's why I said when we take examples, you will understand it. Okay. So let me demonstrate this with some examples. Okay. So for example, any constant force is conservative. Okay, because work done is this path integration actually results in F dot S. It only depends on displacement. No. So for example, we have suppose a situation where okay, in the XY plane, let's say you're going from a point A, which has coordinates A comma B, to a point B, which has coordinates, let's say 4A comma 3B. Okay. Now you can go by one path like this, let's say, and you can go by another path, let's say like this. Okay. But if you're calculating the work done by the force, let's say given by alpha I cap plus beta j cap, where alpha and beta are constants. So the force we are talking about is a constant force. Okay. Then it doesn't matter whether we go by path 1 or by path 2. You can see work done will become F dot S. So it will become alpha I cap plus beta j cap. Okay. Dot product with 3A I cap plus 2B j cap. Okay. It will be the same for any path from A to B. You can see it will be the same. So that is showing that the force is conservative, because in this case it's a constant force. So have you understood this example, Liti? Then we'll come to more complex examples, but just for the sake of this example, you can see this how it will work. Okay. Now, of course, not always things are going to be so simple. We might have a variable force which is changing from point to point, and it's not so easy to show whether it is conservative or not. So we'll come to those examples also. But straight away, you can see that yes, of course, if the force is constant, then definitely it will be conservative, because for any path, the work done will be the same. is because that you can see that the displacement from A to B वो कैसा है, that is this vector na, the displacement from the point A to B is this vector na. So A to B, you can see the displacement is, you learned this in kinematics na? Okay, yeah, understood. Okay. So this example is clear, I hope. Okay, now let's look at a more interesting example. Okay. Now again we are talking about xy plane only. Okay, and let's say this point has some coordinates, let's say 5,4. Okay, so x is in meters, y is in meters. Okay, now a variable force given by F is equal to 2x I cap plus 2j cap acts on a particle at the point x comma y, where the force is in newtons, okay, and x and y are in meters. So this type of variable force acts on a particle when it is located at this position. Now the question is going to show us two possible paths. One path is like this, from the origin to the point P, first going along the x-axis and then taking the route parallel to the y-axis. So this is path 1. Okay. And second, we are going to see a path like this, that first we move along the y-axis from the origin, and then we go parallel to the x-axis to that same point P. So this is our path 2. Okay. So what we have to do now is we have to show that, so calculate the work done by F for the displacement from origin to the point P that is shown by path 1 and secondly by path 2. So we have to calculate the work done by this particular force, okay, for the displacement from O to the point P, but first by path 1 and secondly by path 2. And by doing this calculation, we'll see something interesting over here. So just note down the question first, then I'll explain how to solve this. Okay, so at this moment, just looking at the expression of the force, we cannot guess whether we'll get the same work done in path 1 and part 2 or not, and whether the force is going to be conservative or not. So we are going to do this, not only this, we are also going to show that the force F is conservative and the work done by F will be same for any path from O to P. So now this question is also giving you a hint that we should get the same answer for A and B. Okay. So let's see how this works out. Okay. So this is a more complex level of question. Let me discuss in detail. So what we will do is we will begin by calculating the work done for path 1. Okay, so let's start with path 1. So for that, we'll forget about this path for the moment. We'll just concentrate on this path. Okay, you haven't finished writing the question? Okay, just finish that up first. Okay, so let's come to this. So now see what is happening. So first of all, let's not worry about this part. Okay. So anyway, so this work done from O to P, now, we will first divide it into work done from O to, let's say, this point, which is 5,0. Okay. So work done by path 1, we'll write it as work done from O to A plus work done from A to P. Okay. So for work done from O to A, we will see that if we are at any point in between like this over here, the general coordinate is x comma 0 because we're on the x-axis, and the displacement is along this direction. Okay. And the force will have both the components. So the force is something like this. Because the force was given as 2x I cap plus 2j cap. Okay. So work done from O to A will become what? It will become integration of f dot ds from O to A. So at this point, you can see the force will become 2x I cap plus 2j cap. Okay, dot product with ds. Now you can see the ds while going from O to A, the ds is only one component. It is dx I cap. So the dot product is with dx I cap going from the point O to the point E. So further, when you take this dot product, it will just become 2x dx. So at the point O, the value of x is 0. At the point A, the value of x is 5. So you know the integration of 2x is x square. So x square going from x equal to 0 to x equal to 5. So that is 25. Okay. So this is the work done from O to A. Okay. And next we have to calculate the work done. So this will be in SI unit joules because everything is taken in SI unit. So for the total work done in path 1, we have to calculate the work done from O to A plus A to P. So work done from A to P, integration f dot ds from A to P. So now going from A to P, you're at any point like this. So your displacement is along the y-axis. Okay. And your force will again be something like this. Now at such a point, your x coordinate is fixed at 5 and your y coordinate is variable going from 0 to 4. Okay. So this f dot ds will just become, now your x coordinate is fixed now. So the x component of force is 10 because it's 2x. Okay. Dot product with dy j cap going from A to the point P. So this dot product will just give you 2 dy. Very simple. Okay. Even simpler than the first one. Going from y equal to 0 to y equal to 4. So further now, this dot product will become 2y. I mean, this integration will become 2y from y equal to 0 to y equal to 4. So that will become 8 joules. Okay. So the work done from A to P is coming out to be 8 joules. So now we can see that the total work done by path 1 is equal to 25 plus 8 or 33 joules. So this is just the 1A part done. Now just like I've done 1A, just understand these steps first. Here to here, then here to here, then the sum of these two. And then calculate it for the other path, which was first along the y-axis and then along the z-axis. So try it out for the second path yourself after noting this down. The voice not coming. Is audio coming clearly now? Okay, okay. Okay, so anyway, so the work done from by the path 2 now, we are doing the same thing. We are dividing into O to B plus B to P. Now, when you're going from O to B, at any point you can see your x coordinate is 0. You are at 0 comma y going from 0 to 4. So if your x coordinate is 0, then in this thing now you can see the force's x component will become 0. So the force at this point is just 2j cap. So integrate f dot ds from O to B, it just becomes 2 dy integrated from y equal to 0 to y equal to 4. Understood this calculation? 33 आएगा ना Krish, it should come out to be the same value. Now calculate the work done from B to P. So now going from B to P, you can see that at any point like this, your x coordinate is variable and your y coordinate is fixed at 4. But your displacement is along the x axis and your force is like this. Okay. So F will again become 2x I cap plus 2j cap, but your displacement is dx I cap from B to the point P. So this will now become 2x dx integrated from x equal to 0 to x equal to 5. So that is x square integrated from x equal to 0 to x equal to 5. So this will give me 25. See, Diti, from O to B now, O to B when you are going, at any particular point, what is your coordinate? It is 0 comma y now. So what is your force? It is 2 into 0 I cap plus 2j cap. So this is the expression of. So that's why the force is just 2j cap. And the displacement is along the y-axis. So it is dy j cap. So your f dot ds is just 2 dy. But this is in O to B. Whereas B to P, this is happening. B to P, this is what is happening. So this will be 25 joules. Okay, so again, this is different. Okay, so O to B, this is the work done. B to P, this is the work done. Total is again 33 joules. So it's the same as the work done in the first path. Okay, so work done from B to P is 25 joules. So now once again, the total work done in path 2 is 33 joules. Okay, so ultimately what we are seeing is that the work done for path 1 is equal to the work done for path 2, which is 33 joules. Okay, so this doesn't guarantee it's a conservative force, because for conservative force we have to show that this is not a coincidence. It should always happen this way. Whatever path we take, it should give us 33 joules. So there's still some work to do before we can show that it's a conservative force. But yes, so far what we have shown is that in these two paths, the work done is the same. So this is the first part of the question. Okay. So now coming to the second part, how will I prove that this force is conservative? Okay, finish writing this down. Okay, now let's come to the last part of the question. So again, important concept to learn from the last part of the question. How do we show that the force is overall conservative? Okay, to show that work done by this force is path independent. Okay, and therefore the force is conservative. Let's see how that will happen. So any two arbitrary points we can take as the initial and final position, where the coordinates are x initial, y initial, and x final, y final. And any arbitrary path we select, any path. The work done by this force, which is given by this formula, okay, what should happen is that F dot ds from initial to final should come out independent of path. This is what we want to show. Okay. So now substitute. So at a general point over here, let's say my coordinates are x comma y. So the force acting on the body is F like this, or on the particle or whatever. And the displacement is not in any particular direction. The displacement is continuously varying in direction. So we can write the displacement as dx I cap plus dy j cap from a general point x comma y. So for a general displacement like this at the point xy, F dot ds is becoming how much? It is becoming the dot product of the value of force at that point, which is given by this formula. Okay, this is at x comma y. Okay, so it is 2x I cap plus 2j cap dot product with the general displacement, which is dx I cap plus dy j cap. So this is a little bit more complicated than what we did in the previous part, where we were displacing only along the x-axis at one time or only along the y-axis at one time. Now we are having a general type of displacement. So this relation becomes 2x dx plus 2 dy. So this is my f dot ds. So therefore work done, which is this integration, will become so this is becoming integration of 2x dx plus 2 d from whatever initial position to whatever final position. So this will be x initial, y initial to x final, y final. So next step, what we will do is we'll break this integral into two parts. So the first one is x dx, second one is this, and this is going from x initial to x final, and this is going from y initial to y final. So you can see that this is so now we're getting a particular formula for the work done, a sort of general formula for work done by this force from any initial to any final position. Okay, so in this general formula, okay, we can see that the work done depends only on these coordinates. It only depends on this. Therefore, it is independent of path. It is independent of path. It's the same for all paths between these 2 points. So therefore, the force is conservative. So we can see that while all constant forces are conservative, but even variable forces can be conservative, like in this particular cases. We can always have a situation where the force is variable, but it is conservative at the same time. Okay, so hope all the steps are clear in this. So this is an example of a conservative force. A more complex example of a conservative force. We've already seen that any constant force is conservative. Now, kinetic friction is a non-conservative force. And let's see why. Yeah, Prince, I just gave example of conservative force. Na? Abhi to any constant force is conservative. Then the other example we were discussing, that also turned out to be a conservative force. So I've already given you examples of conservative force. Now imagine this is a this is a rough horizontal surface. Okay. Now a particle is being pushed from this position A to this position B. Via two different paths. One is a path like this, and the other is, let's say, a path like this. Yes, we will come to those examples. So that's the example we are taking. The kinetic friction is a non-conservative force. That's the example we are doing right now. So suppose this coefficient of friction is mu. Okay. So now a particle of mass m is pushed from the point A to the point B by horizontal external force by two possible paths. Okay. Path 1 is a straight line path, and path 2 is, let's say, a semicircular arc. Type of path. Okay. So calculate the work done by friction in each case. In each, and show that kinetic friction is non-conservative. Okay. Take the distance between A and B to be D. Take that variable as D. M is the mass. Acceleration due to gravity is G. And the coefficient of friction is mu. So just try this out, people. Okay, so you can see that whatever type of path the body is moving in, okay, the forces on it will be such that, let's say anytime the particle is here, mg acts vertically downwards. Normal reaction is acting vertically upwards. Okay. Whatever external force you're applying on the body, that will apply tangentially along the surface. So what about the kinetic friction? It will act tangentially like this. Okay. So if we take the top view of this, in the first path, we're going directly from the point A to B via a straight line path. So as you're moving from A to B, at any point when you are in between like this, your displacement will be in this direction, and your kinetic friction, which will be mu n, will be in this direction. So the kinetic friction, which will be mu n, will be such that its magnitude is mu mg. So therefore, in path 1, the work done by friction will be this dot product. So it will be minus mu mg ds integrated from A to B. Now this integration is nothing but the total straight line. So it will be minus mu mg d. Okay. Because here integration ds will be the path length. This integration ds from A to B, it will be the path length from A to B. Okay. But for path 1, that is a straight line. Okay. So therefore, this integration from A to B by path 1, it will be nothing but d. So that is the work done in path 1 is this much. Now note this down, then we'll come to the second path. Let's finish this stage, then we'll scroll up again. You have a lot of time to write down the question. Just finish writing this down. I'll take you back to the earlier picture. Okay, so you can understand why this is like this, because you can see now when it's moving along this path, even the straight line path here, as your particle is moving from A to B via this straight line path, at any point of time, the normal reaction is only equal to the weight. These two are perpendicular to the surface. There must be some external force which is driving it along that path, and friction acting this way, so that its displacement is along the path. Okay, so this kinetic friction is mu m n, and n is equal to mg, because F is only acting because it said that by some horizontal external force. So that's in the horizontal plane. So normal reaction is not affected by it. Okay. Now let's come to the second path, which is the curved path. Now see, when you're going along the curved path, let's say at some point of time like this, your displacement is in this direction. Your differential displacement is in this sort of direction. So at that point of time, the friction acting on the particle will be like this. It will be opposite. So again, the friction vector and the displacement vector are opposite each other. So for the second path also, the semicircular path, as you're going from point to point, you can see that always your differential displacement and friction will be in opposite directions. Okay. Excuse me. Okay, it will be this from A to B. Now this time, this is the path length for the semicircular path. So this will be how much? It will be equal to pi r, where r is d by 2. The total distance was d. This was d. So d is also the diameter of the semicircle. Okay. So work done by friction will become minus mu mg into pi d by 2. Okay. So this is path 2. So now you can see that work done in path 1 is not equal to work done in path 2. Okay. Because work done in path 1 is minus mu mg d, and second path is minus mu mg d into pi by 2. Now pi by 2 is greater than 1. No? You can see pi is 3.14. So they are not equal. So that means the friction, kinetic friction, is showing the property of non-conservative force. So therefore you can see that kinetic friction here is a non-conservative force. Okay. So some examples of non-conservative forces. friction, I mean kinetic friction, which we just seen just now. Okay, then there's something called viscous force or viscosity. Okay, it acts in fluids, but we will discuss it at a later stage, and you'll see that it's also a non-conservative force. Then things like air drag forces. Okay, these are all examples of non-conservative force, whereas examples of conservative forces will include spring force. We'll discuss about these in the next lecture. Gravitational force. In class 12th, you will learn about something called electrostatic force or Coulombic force between charged particles. These are all going to be examples of conservative forces. Okay, people, so hope you have understood through this example how kinetic friction is acting like a non-conservative force or showing the properties of non-conservative force. So we will conclude today's lecture here, and next time we will discuss more about conservative, non-conservative forces, and then about potential energy. We'll learn the other type of mechanical energy, which is called potential energy. We've already learned about kinetic energy, and we will see that there's a certain relationship between work done by conservative force and potential energy. So you can read ahead from any reference book like NCRT or Resnick Halliday or even H.C. Verma about the next part we'll be learning, which will be about potential energy and conservative forces, and you can continue doing problems from HCV and your module. Okay, that's it for today, people. Wish you all the best.